Okay. Hello. Okay, let's get started. And this time we talk about the quantum counting algorithm, which is a bit of application of the Grover search algorithm. And today we are going to switch direction. So there are more applications of Grover's algorithm to come. But today we are going to switch direction and talk about the lower bound of the search problem. So we have seen that the Grover search problem is Grover search is not a problem, although it's kind of mixing the two things. Okay? But technically, Grover search is an algorithm. It's upper bound to this search problem. So it says that there is this quantum algorithm that can solve this search problem with order square root and with order square root and query and also computation time. But now the natural question is to ask is this the best you can do with quantum algorithm? Okay? So what is so the technical term to say this is that what's the lower bound on the search problem? So what's the fastest quantum algorithm that we can design to do this search problem? And today we are going to prove that Grover's algorithm is actually optimal. So any quantum algorithm that you use to do this search problem, you need at least omega square root query. And because each query is one gate, this also means you need at least omega square root time. Okay? So Grover's algorithm is indeed optimal. Okay? And I guess today this will be the most theoretical part of the course is how do we do lower bound. And traditionally it's usually it's very hard to do lower bound on complexity theory, just because there are infinitely number of algorithms you can design. So how you show that you actually need to do a lot of steps to compute your thing. Okay? But here we see that in terms of quantum query complexity, because we are in this query model or oracle model, then we can pretty precisely say that what the algorithm become when you do some oracle code, and in return we get a very nice precise theoretical lower bound on this quantum query complexity. Okay, so but let's come back to the search problem and let's see how we get a lower bound on this quantum search. And as we say, we will want to get omega square root and lower bound. Okay, and now we are being a bit funny here. So it's a lower bound for search, but we don't actually bound the search problem. Search problem says that find x such that f of x equal to 1. Okay, and we actually bound the easier problem, which is a decision problem, where we say does there exist x or not exist x. Okay. So we lower bound the decision version of the problem, and it's an easier problem. So if deciding this problem is very hard, then you know deciding this problem is even harder. Okay. So let's bound this easier problem. It's a decision problem. So and I guess there is a 0, 1. So let's say we have some big F. Let's try to decide your small f. Okay, so this is big F equal to 0, this is big F equal to 1, something like that. So this is a decision problem, you want to output 0, 1. Okay, and so I guess it's here. So so this is our big F. Does there exist x or not? Okay, so if f of 0 equal to f of x equal to 0 for all x, then we say it's no. And there is some x such that f of x equal to 1, then it's yes. Okay, so input is this small f, and output is something we didn't write here, but it's we can call it a big F. Okay, so it's a bit confusing because there are two f, but yeah, that's what happens when we have oracles. Okay. And anyway, yeah, so I guess the very high level idea of the how we do the quantum search algorithm is we think about algorithm that look like this. So yeah, we have said this several times. So in a quantum search, in an oracle algorithm, we can always think that we place the oracle inside our circuit one by one, sequentially. And yeah, because even if it's parallel, you can just think about you are placing them in sequentially and with some swapping in the middle. Okay. And so you just placing the oracles one by one, and then you have some unitary in between them. Okay. And those unitary can be whatever unitary, but those unitary don't depend on your oracle. So those U0, U1, U2 to U big T, those unitary determines your algorithm. And what does your algorithm should do? And so now we have, I guess, a Boolean function to calculate Boolean big F. And at the end, so your quantum algorithm will do this, and at the end it will do some measurement. And this measurement should tell you 0, 1, and 0 means there is no mag item, and 1 means there is a mag item. Okay. So yeah, so your algorithm will change the quantum state. So your algorithm will change your quantum state like this. And yeah, so the idea is that when an oracle has no mag item, it will give you some quantum state at the end. And when your oracle has mag item, it should give you some other quantum state at the end. And those quantum states need to be pretty far away for your measurement to distinguish it. Okay? So there are two things we do in this thing. So we will say that in each time you do this oracle call, the quantum state can only change its quantum state between the no instance and the yes instance can only change so much. And also at the end you need to change a lot, so you need to go through a lot of steps to make enough change between this 0 instance and the yes instance. Okay, and yeah, so the important thing here, one of the important thing here is that all those U, they are quite arbitrary, but they don't contain oracle codes. So all those U cannot tell the difference between yes and no, because you do the same U between the yes instance algorithm and the no instance algorithm. Okay, yes instance and the no instance are only distinguished by all those oracle codes. Okay. And that's a high level idea. And yeah, I think yeah, previously I have a lot more high level idea, but I think we can now jump straight into the proof. It's probably more clear. So let's talk about mode notation. So I have this mode notation here. And yeah, so we say we want to track the quantum state, so we have some name for those quantum state. So we say after the first unitary, the quantum state is called this psi f0, and then after the first oracle call and the second unitary, this is psi f1, etc. Okay, and at the end, the state is psi ft. Okay, and yeah, and this f will change when you put a different oracle. So this f is small f, and remember the small f is basically the content of your oracle. Okay. And yeah, and so now we need to choose some small f that's easier for us. Okay, that's because so here we want to distinguish between no instance and yes instance. Okay. And there is basically only one no instance, so there is no choosing here. And this is a no instance. It's called f0 tilde. Okay, it's for 0. Okay, and we need this tilde here because one instance we also named something very similar. Okay, okay, so there is a no instance. This is O0. So remember, yeah, O instance is the truth table is O0. And the yes instance, there are many yes instances. Basically, every other f, small f is a yes instance. But we want to choose something that algorithm that is very hard to distinguish between yes and no. Okay, so we choose those instances that looks mostly like O0, that is only have one mark item. So in your truth table, only one only one location is 1, and all other directions are 0. And there are n slots, so there are n different fx. Okay? And yeah, so we define those fx as with x from 0 to m minus 1. Okay, so yeah, so this is why it's a bit tricky. We count x from 0 to m minus 1. So we cannot have f0 here because this f0 will be same as this f0, so we have tilde here. But anyway, we count x from 0 to m minus 1 because there are a different input value from 0 to m minus 1. Bigger and different input location to small f. So remember this is just a notation. So small f is 0 to m minus 1 to 0, 1. Okay, and yeah. Okay, so this is our notation. We count from 0, and yeah, and we have this small f sub x with x also from 0 to m minus 1 as a particular function where it's the truth table is all 0, but at the x location is 1. So it has that f sub x of x equal to 1, and yeah, so this one here, and f sub x of y equal to 0 for all other y. So you have all other 0 here. So x is a unique mark item of this f sub x. Okay, so yeah, so we have these two notation. Okay. And yeah, and then we will consider. Okay, so there is and then we see that there are actually a lot of difference. So we kind of gloss over this because there is one no instance, but there are many yes instances. And when we talk about distance, well, we can have distance between two quantum states, but there are many quantum states which distance we mean. And actually what we mean is we want a distance between all of them. So we want a distance between them and sum together. So there is one no instance, this thing, and there are n yes instance, this thing. And we sum over all the n pairs of them, okay? Because, okay, so there is one of this and n of those, and there are n pairs of them, okay? And yeah, so we will consider this difference in this psi ft between all n pairs, okay? And but that's a bit of the next slide. I guess we can show the next slide. So we will consider this is our progress. And actually the distance is you just take the quantum state, calculate the distance and square. Then we sum over the distance. And so that's our progress function. And but before we can talk about this, we want to say a little more on our notation. And so first notation we want to use is I guess to say that notation we don't yeah, we can probably talk about this first, okay? And yeah, so yeah, I guess sorry, we still need notation, and so it's just a bit simplifying notation. So yeah, you see that this we have this f sub x and f0. Yeah. And now think about what are the, we have all those oracle code, right? We have all those OF, and what are all those OF? And all f0 tilde, we have a really complicated notation here, and we see that we have complicated notation here. It's okay because very soon we don't need to write it. Or f tilde, f0 tilde is going to be identity because we are considering the phase version of the oracle. Okay. And I guess here we are doing a bit of I guess it's not really in homework, but something you can think about. Okay, so we are being lazy in two parts. Okay, and I think it's actually in the book. I'm not very sure. Okay, but anyway, we are being lazy in two parts. For now, just assume it can be done. And if you believe me, this can be, you can generalize it to more general version very fast. Okay, so the first lazy thing we do is we assume our oracle is the phase version. And remember, this phase version of oracle is actually a a bit weaker than the computational version because we don't have the control register, but that's okay because you have, I think if you do 2 of this is equal to the control version. Good. So that's the first lazy part. We assume our oracle is in phase version. And if our oracle is in phase version, then yeah, then it's all f0 tilde is just identity because all of the f of x equal to 0 here, and they just have all f of x equal to x. And so this is identity, so we don't need to care about all f0 tilde because it's identity. So in the known instance, you know all those things are identity here. Okay, that's the first thing. That's nice. Okay, so let's mark it a little bit. And yeah, and then we also want to know what's all f of x of y. Okay. And yeah, for definition, we don't actually need for the definition of a progress function, we don't need to do too much. For the purpose of definition, we just need to see that this thing is indexed by this small x. We are indexed by small x from 0 to n-1, so might as well just call it Ox. Okay. So later on we will say Ox equal to so this is a simplifying notation here. We just say Ox equal to O f of x. And so that simplifies notation. And I guess that's a jump to different part. Okay. And so this is notation. So our algorithm, and our progress function now. Yeah, so now with these two notation, we can define our psi kx and the psi k. So psi k will be the quantum state correspond to the known instance. And so this k means that it's on the case step. So back to here, you do k step, then you have psi k. Okay. So after the I guess after UK, which is actually after k oracle calls and k plus 1 unitary. Okay. So after UK, you have psi k, and I guess you can have psi kf, and then when f is f0 tilde, then we just omit the superscript here and call this psi k. Okay. So psi k with no superscript means that your oracle is all 0 string, and basically you don't do any oracle call here. It's just 0 and act on by all those unitary. Okay, and then we also have psi kx because we know the yes instance is indexed by just x. Okay, so I guess here the real important thing here is yes instance are indexed by this x. So let's give it its own highlighter. So x is the index of everything, x from 0 to n-1. Okay, we have those x, and so yes instance are labeled by this x, and so we really don't need to say psi k f of x. We can just say psi kx. Okay, so psi kx correspond to this oracle, and if you write it out, it's also this Ox where we already omit the f here. Okay, so so psi kx is just when only mark item is on the x location. So once again, write x is in this 0, 1 to n-1 state. Okay, so there are n different x and different possible unique mark x, and so this is when oracle is marked on the case location, and x location, and after basically k oracle calls here. Okay. And then we have those two states, and as we said, we will define a progress function. Progress function is the difference between them, and so just this difference is you just take the look at the quantum state. Quantum states are complex vector. You can do subtraction on complex vectors and take their known square. Okay. So it's a very brute force distance, but it works. Okay, so we take this brute force distance squared, and we just sum over all x. And as we say, x is from 0 to n-1. and this is what we call the progress function. And we have basically three things here, okay, although we only these two. And the first thing is very simple, so D0 should be 0 when you have a no-local call at the very beginning. So D0 is this thing at the very beginning because there is no local call, so every side should be set. So D0 is 0 because every side is the same and they just sum over 0. And then there are two things that we actually need to prove. One is that this dk don't grow too fast, actually it grows quadratically. So dk will equal to order k squared, and this is, and so those two things are both true for any algorithm, so actually any u. Okay. And yeah, so dk equal to order k squared, and so this is each oracle call, your progress function don't grow too fast, and also d big T equal to omega. It means that at the end of algorithm, you want to have a good probability to distinguish between the yes case and the no case. Then yeah, then this dt needs to be omega n, and I guess intuitively you are summing over n terms, means that so each term need to have a constant probability to distinguish. So each term should have a constant distance, so you sum over n terms, it should be omega n. And then you combine those three facts, you get the big T needs to be at least omega square root n, so it needs to be like a squared of square root n to be n. Okay, so that's a high level idea. Any questions so far? Okay, if not, then yeah, let's dive into the technical part, and let's go back to the previous page of slide. Okay. And so here we have a bit of a calculation here, and already calculated f0 or f0 tilde is identity, and we also simplify OX here. So OX is well, it has only one mark item, so you think about O of x on y, then it give you a -1 only on x. Okay. And then you think you can, and it's something we are pretty familiar with. This is reflection around this computational x. Okay, so it can be written as this identity minus 2xx on y. Okay, and yeah, so you see this thing and this thing, and then because this works on every y, you see OX is just identity minus 2xx. Okay, because when, so you can just do checking again. So when y don't equal to when y don't equal to x, then this is just y because it's identity on y. And when y equal to x, this is y minus so this is x minus 2x, so it's minus x. So you get this -1 here. Okay. So yeah, so we have OF0 tilde equal to identity, and OX equal to identity minus 2xx. And yeah, now let's do calculation. Okay, so we want to say this thing, and as we said, so this actually includes this, and the first step is calculate D0, and as we said, D0 is 0. Okay. And then we'll down to prove this by induction. But I guess the more intuitive way to see this is not looking at this, but we want to look at the growth of dk on each k. So we want to look at the difference between dk and dk plus 1. That's the thing we want to see. Okay, so what's the difference between dk and dk plus 1? dk plus 1 minus dk. And we want to have an upper bound on this thing. We want to say on each step it don't grow too much. Okay. And yeah, so let's start try to write the dk plus 1 as dk. And to do that, we want to write this psi xk plus 1 and the psi k as from psi k and psi xk. Okay. And yeah, and so let's write it out. So so we see this thing is so this psi k plus 1x, psi xk plus 1 is this thing, so it's when you increase k, you just add more unitary on this. Okay, and here you see that I guess k plus 1 you have 2 more terms here. So yeah, so this is psi xk, and you get k plus 1, you get 2 terms here, 2 more terms here. You get the extra ox and uk plus 1, because on each k you see that you get 2 of them, 2 of them, 2 of them. Okay, and similarly for psi k, so for psi k is even simpler, you just get the extra u. Okay, and so we write it out, is dk plus 1 is summation x, and then you have uk plus 1 ox, and then your psi k x, and then uk plus 1 psi k and the square. Okay. And then here the first nice thing happened. Then here nice thing happened because we see that we can get rid of uk here. Okay. And what can we get rid of uk plus 1? Oh, sorry, uk plus 1. So we can get rid of uk plus 1 here because well, it's a unitary, and we can get rid of uk plus 1 because it's unitary, and unitary doesn't yeah, unitary preserve length, and you have length square here, so yeah, so you have 2 constant state multiplied by this unitary, and yeah, unitary doesn't change length, so you can cancel both unitary here. So you get just ox, psi xk, and psi k. And also I guess I forgot to say 2 things. And here the notation is even a bit lazier because you don't write ket here, so it's a bit confusing what's inside. But what's inside is a matrix multiplied on a vector, and this is a vector. Okay, because yeah, we're lazy, so we don't write a ket on our vector because there are too many vectors. So psi k is psi k ket, and psi xk is psi xk ket. Okay, so this is nothing but just we are being lazy here. And also another thing we are being lazy is yeah, so actually we kind of already got over this. Okay, and another thing we are being lazy is basically we restrict our algorithm onto this, so we think our space are just this computational basis for x. Okay, so we think our space is just an n-dimensional space that has this basis of x. Okay, but in general, you have algorithm, so you can actually have more qubit here, and those unitary will also act down the ancilla. So in general, you can have ancilla things here, and your all are only act down part of the space. Okay, but for simplicity, we assume there is an ancilla, and yeah, so this is something you can check maybe in homework, that actually yeah, even though we only do this with no ancilla, it's very easy to generalize to case with ancilla. Okay, but now focus on yeah, let's go back to our derivation. Okay, so our calculation of dk plus 1, and in this simplified case, and we say that it's just equal to this sum x, ox psi xk minus psi k, and then we do something smart, and I guess there's no good explanation of why. I guess there are some explanation, but really it's just something smart we do here. So we add and subtract a term in the middle to make to break this into 2 terms that are easy to manage. Okay, so yeah, so I guess a very high level idea is you have 2 terms that depend on x multiplying each other, and 1 term that don't depend on x on it here. And it's annoying because you want difference between something as x and something don't have x. So we add a subtract some term with 1x on it. Okay, so we subtract this ox psi k term. Okay, in the middle. Okay, so yeah, so we subtract ox psi k, and we add ox psi k here. Okay, and yeah, because each term we add subtract this, so this is adding 0, so this is totally set. But then we can group things together. Then we have ox on this difference between psi x and psi nothing, and also we have OX minus identity on psi k. Okay. So yeah, so this is a small step. We subtract this OX psi k here. And then now it's just a more brute force calculation now. Okay. Yeah, so now we have summation of a whole bunch of terms and a whole bunch of non-square terms. And we have a non-square term of two things. So you remember, so this is still a matrix multiplying on a vector and a matrix on vector. So this is a vector and a vector. So let's call this vector B and this is vector C. And it's easy to show, and it's easy to show that vector b plus c square is less equal to b square plus 2bc plus 2 non-b non-c plus c square. This is just, I don't know, some matrix algebra. I guess you have some Cauchy shorts for the cross term here. Okay, and anyway, this is true for complex matrix. And yeah, so that's we just do expansion on this. Okay. And so B is this thing and C is this thing, and want to check what are there no. Okay, and so C is easier, so let's do C first. So and yeah, so we have C is this thing here, and calculate C. Well, I guess we haven't calculated non here, but we calculate what is we simplify C here. Okay. And so now we use our OX equal to 2 minus I minus 2xx. Okay, so this is several steps ahead. Okay, so OX equal to this thing. Okay, so we only need this here. Okay, okay. And OX equal to this, then we see that identity minus OX is something very simple. It's or actually OX minus identity is we'll get rid of this identity, so it's minus 2 times xx is the x projector on psi k. So yeah, and you can move things around. So now let's get back the k notation. Remember, psi k is actually a ket, so this is minus 2 and with some number times this computational basis x. And the number is the inner product between x and the psi k. Okay. And so now we can write our dk plus 1. So it's this thing, and then we use our I guess triangle inequality. Not quite triangle. Guys, this is a square expansion, and we see that it's less equal to now the first term square, so b square. And then we jump a few steps. So b square will also use this identity again. So we use that when you take a norm, we don't care about OX here because OX is also a unitary. Okay. So norm b square is just norm psi kx minus psi k square, and then we have yeah. So yeah, I guess we can write here. So what we use is norm b equal to this psi xk minus psi k non square. Don't have square here. Okay. Yeah. So we have norm b equal to just this norm. We can get rid of OX because when you take a norm, the unitary doesn't matter. Okay. So OX you can also get rid of. That's very nice. And okay, so norm b is this, norm c is this, and we can just write things together. So norm b squared, and then in the middle, yeah. So norm c is this, norm b is this, and in the middle we have 2 norm b norm c. So 2 times 2 equal to 4, and norm b. Do that, and this norm here and this norm here. Okay. And yeah, oh, I guess I should say norm c. Okay, so when you see is this thing and you take norm c, you have the minus sign goes away, and x is a normalized vector, so norm c is just 2 times the norm of this inner product. Okay. And yeah, so b squared plus 2 norm b norm c plus norm c square. Okay, norm c square, you have 2 square equals 4, and this thing square. Okay, and so we see that we are getting close to something we want. So So we get our dk plus 1 minus dk here because this part is dk. Okay, so this is very nice because so you take out this part and the sum over x, then you see that we have dk. Okay. And so the remaining part is our dk plus 1 minus dk. Okay. So I want to say this all those things are not too big. Okay. And yeah, also we already see that on the first step we already cancel our uk. So if we can, so when we bound this thing, we don't care about our algorithm because dependence on algorithm actually got cancelled on the very first step. Yeah, so it's very nice. We just need to bound this, and I guess yeah, but that's kind of a lie because the explicit dependence on algorithm is cancelled, but we still have a dependence on algorithm that is those psi k x and psi k here. But the nice thing here is, yeah, you might say this can be arbitrary thing. But the nice thing here is actually you are able to bound this for whatever psi k x and psi k. So even when you choose the worst possible psi k x and psi k here, those things here will not be too big. Okay, so that's kind of the trick. Okay. And but anyway, so that's a high level idea, and let's see how we do this. We actually need to be a bit more careful. Okay. And yeah, so we don't actually directly calculate this. We go back to our induction. But anyway, so you see that so this is dk, and then we have this part is also kind of like dk. And then we have the other part that basically just change how fast we can go up. Okay. And yeah, so we kind of want to see what is sum x then x psi k squared. And turns out this thing can be very nicely bounded. Okay. So this thing is well, so this is anyway, there are different ways. But anyway, different ways to see this, but it's easy calculation. So this known inner product square is well, this is a complex number, and the known square is it, and times its complex conjugation. So yeah, and then we sum x, and now we can do some I guess linear algebra. We see that the only dependent on x is the middle part, so we can have summation over the middle part first. And summation of middle part, and because well, here is kind of we use no and theta, so we sum over x, and x is everything. So we sum over x, this is the identity matrix. So we just have psi k multiplying on identity matrix plus psi k, and so this thing equal to 1. So for no matter what your psi k is. Okay. So I guess this is a nice part of this proof, where we get rid of dependence on psi k, because you see that after you sum x, this is this equal to 1 for psi k. No matter how bad you pick your psi k, it will be 1. Okay, and yeah, so it's yeah, you can have more interpretation, but basically this is the smart or average part of the algorithm. This is where you see that you erase the dependence of really erase all the dependence of your algorithm, because you average over all x, so your algorithm cannot just guess the x, etc. And anyway, let's get to algebra. So we have bound what's this sum x and this known x psi k square. And now we need to do something smart a little bit. Okay. Now this is just pure math. We have bound this term, and we want to take a difference to this term, and we have kind of a closed term in the middle. And what we do here is we use Cauchy-Schwarz inequality to make things nicer. Okay, so we say, okay, so yeah, we basically use Cauchy-Schwarz to disentangle the middle part. Okay. And let's see how this works out. So we have yeah, so this requires some thinking, but we have the solved out result here. So we have sum x, ax, bx is less equal to so we think about ax as a vector, indexed by x and bx as a vector indexed by x, so this is the inner product between a and b, then it's less equal to non a times non b. So non a is some x and the absolute value of ax squared, then some square, then take a square root. Then also for vector b, you have this some square taking a square root. Okay, so these are Cauchy-Schwarz. And then we have Cauchy-Schwarz here, and we can let's see what we do. So this is what we have. So dk plus 1 less than the sin x, then b squared, 2bc, and c squared. And let's see. Oh, okay. And yeah, so we just use the Cauchy-Schwarz to break the middle term. So first term, as we said, this is dk, so this is quite nice. And then in the middle term, we want to break into dk term and the other term. Oh, I guess let's say the other term. Okay. So the other term we say we already bounded. Okay. So we know it's the sum of x it just become 1 and times 4, then this is 4. Okay. And the middle term we break with Cauchy-Schwarz. So we have some x, and so this thing is ax, and this thing is bx. Let's write it here to be clear. So this is ax, and this is bx. Okay, and now this is just we'll write down the formula. So square root, then some x, and we have ax squared, and square root some x, and bx squared. And but we already know what sin x, ax, this is sin x a squared, this is dk. So we have square root dk here, and this thing is 1 because this thing. Okay. So yeah, so this thing is dk plus 4 square root dk plus 1. And yeah, so this is basically we see how it progresses. So we get dk plus 1 is less equal to dk plus 4 square root dk plus 4. And then from here, it's just a bit of math. So you see that the change in dk, is basically this square root dk. And this will give you dk will grow quadratically, and we have easy proof here is yeah. So we have easy wrap-up proof here. We say that we prove that this by the induction. We know that the dk will be less than 4k squared, and so we just show this by induction step. First step, dk is less than 4k squared, and on here so if this is already satisfied on k step, then on k plus 1 step we can bound it. So here we use I guess induction. So here is induction. We have dk less equal to 4k squared, and so we can bound all those things. So dk less than 4k squared, and the 4 squared, and the square root dk will be less than equal to 2k, and so this is 8k, and we plus 4. And we see that all the numbers here set out nicely. This is equal to 4 times k plus 1 squared. Okay. And yeah, so dk plus 1 is less equal to 4k plus 1 squared. So by the induction step, then we have this thing. And yeah, I guess the induction is here, and I don't really need to write here. Okay, so yeah, that's the upper bound. Any let's see how much we want to do. And I guess we I want to stop early today. Anyway, any question on the, I think, will depend. I think the hard part. So this part is the part where we actually deal with Oracle, and the other part is actually a bit of quantum information theory, but don't have that much to do with complexity theory. That's just some measurement probability thing. Okay. But any question on the core part of the proof? So this is where we bound the progress function with the number of Oracle calls. So dk is order k squared. Okay. If okay, then I guess let's take a 5-minute break and let's come back at 4:25 and let's try to do the other part of the proof where we'll go to a bit of information theory to show that you want to distinguish these two instances, then then you need to have the difference to be pretty big. Okay, so let's take a 5-minute break. And oh, I have the wrong window here. Okay. I should, anyway.休息到25分。我偷看一下课本。 有没有这一题啊？这个是题目还是他直接讲？忘记了，找一下，订不到。对啊，
这是原本应该就是两个块块算的 Grover 这样。
那也可以啊，一时之间没有想到要加什么。我看一下 ，NC 啦。
曾经有跟证明有关的东西。
好像没有成功的出来。课本有课本的，我觉得课本的题目好像不是没有趣呢。你看一下，但是可以想一下有没有相关的呢 case single solution。deviation。别说呢。可以出个很啰嗦的东西呢，会让大家爆炸的。课本好像没有说，可以出看吧，是一个 notation 大爆炸的东西，就是我们这里的 proof 都假设是没有人 C 的，就其实也不难的东西，但是会让人写很痛苦的，就让大家全部重整一次，然后假设有人 C 的，就是有人 C 的 register， 会 notation 大爆炸，但其实没有难整，我记得，就是都差不多。可以考虑加一题，然后看你要不要帮他们写一点 notation 上去，让他们简单一点。
是啊，应该就是，
我记得好像有一个地方会有个小小的差异，但是其实差别不大。就基本上你就是要写多写很多字这样子，就是你要假设怎样，好像就是你要假设有一个 state 吧，你就写成就是 instead of 这个上 x， 你会上 x， 然后有一个 alpha x 在 c 啊那里之类的，然后一切都会很啰嗦这样子。对，就是你会，就是本来你的 sin x， 本来的 sin x 是，我想想看要怎么写。sin x 本来是一个什么上 alpha x， 好，这样写蛮烂的，但是然后会变成，我换一下好，反正是这样的东西嘛，然后加成 c 啦之后会变成这种感觉的东西。虽然说我们也没有 explicit 用到这样子啊，但是你会变成你要假设 sin x 是，我记得是这样吧，通常是假设成这样子就可以 x， 然后 sin x 这样子。还是把 alpha x 接下来。但是如果你够偷懒的话，你可以把 alpha x 乘到这里，然后变成然后 normalize 之类的。但是对会变，大概会变这样子，然后，我觉得应该做得出来。有类似的计算，可以应该做得出来吧？让大家试试看。就是加很其他的状况。我看看，今天我想要提早下课，应该蛮快。然后可能我们课没有塞教了，可能可以请你 便宜做做看。我找一下 Firefox 888之前围城没有做的slide做一下，就是在哪？这里吗？不见了。真是麻烦，依然要重新 login。但是就之前还有一些乱七八糟的，就是 go over 就是社区的这一些东西，可以把它打成 slide。就是之前旧的手写 slide 其实还有一篇，可以去打一下。我找一下啊，计算概论。这个东西吧，这篇可以让你去打打看。有一些东西，我觉得，对吧？有这个表格蛮不错的，可以打一下。这个整理的表格，可以打一点吧。这个有10页我好像写了一个很啰嗦的 algorithm， 那个是还好，我看可以帮我稍微打一下吧之类的。对啊，对啊 ，OK。好，那我们开始上课，然后应该速教完。对，哦。And yeah, let's back to our lower bound. Where are we? Here. Okay, so yeah, so proof of lower bound. Lower bound of the search problem has two parts. First part is proving that the progress function don't grow too fast. And another part is showing the progress function is really large it's pretty large if you want to get a correct answer. Okay. And the last part don't have anything to do with quantum oracle. It's just when you measure quantum state, you want to distinguish them. Yeah, they need to be pretty far away. Okay. And so this is a bit of information theory, but yeah, let's first give I think the textbook. I think the textbook proof is kind of bad, so this is a deviation from textbook. But anyway, and anyway, here is one. Today we will do the easier version, and I think because we are pretty good on schedule, so after we do this, then we will stop today, and we'll continue on Tuesday for the other two proofs that give us a better bound. But yeah, today let's finish the proof and see bound on this thing and get a flavor of this thing. Okay. And anyway, what we want to show is that when k equal to at the end of the algorithm, we want to have this progress function d of big T is pretty big. Okay. And so let's first characterize what we do at the end of the algorithm. Okay. So well, at the end of algorithm, we are doing a decision problem. We want to output 0 and 1. Okay. So basically, we need to do a two outcome measurement. So yeah, so we need to do a two outcome measurement. One outcome give you 0, another outcome give you 1. And now we need to go back to chapter 1. Chapter 1, we have this equivalence between generalized measurement and projective measurement. And yeah, and we have this equivalence says that you have a generalized measurement. You can do projective measurement with HRR and CLA. So at the end, we can just assume that we are doing projective measurement. Maybe a larger space doesn't matter. You have a two state, and yeah, you do projective measurement on them. Okay, and I guess here if we are, yeah, I guess we can be a bit more careful. Okay, so let's say we start with what we're actually saying is that we have we have two state. Does it make sense? Yeah, I think it makes sense. Okay, so we need to check a little bit extra here actually. So we have okay, keep writing alpha. So it's alpha. We have two state alpha and beta, and okay, and we have alpha and beta, and we are saying we are doing measurement on alpha and beta, and alpha beta, and maybe you have measurement and 0 and 1 on them. Okay, and then what we are saying is we go to a bigger space. So we add some 0 after alpha, so we have alpha tensor some 0 with some number. So this 0, maybe that's a tensor something, and to beta tensor 0 something, 0 to some power. Maybe what's a good name? Maybe L. Okay, and then on this bigger space we do our P and I minus P. Okay, and we are saying the measurement probability of using those two states on this measurement is saying those two states on these two measurements. Okay, so what's the little subtle point we should have checked is that we need to make sure that the distance between those two states, I guess it doesn't matter. Should be okay. So distance between them can be a little different from distance between them, but I think you can, you can easily show that this different square and this different square are the same. Okay. Because when you square and when you have extra zeros, then it's the same. So that's right. Maybe let me see. Do we have blank space? So what I'm saying is alpha minus alpha tensor. Oh, sorry. This way. Okay. Alpha tensor 0 minus beta tensor 0 square equal to is known of alpha minus beta tensor 0. Let's write all the tensor square, and I think then by the matrix multiplication rule of tensor, then this is the first register square plus the second register times the second register square, and the second register square is just this 0 vector, and it's 1. Okay, so that's a bit of a proof. And anyway, go back to here. We have argued that we can just use projectors as our measurement. So we have projector P and projector 1 minus P, and by projector we actually mean Hermitian projector. Yeah, and so let's assume at the end of our algorithm we can distinguish our 0 and the yes case with some good probability, some constant probability. And here we pick the constant a bit larger because our proof is a bit too simple. Okay? And so on Tuesday we'll give a better bound here, but here because we have a worse bound here, so we need a bit of a bigger constant here. But really the constant doesn't matter because this is a decision problem. So any constant can be boosted to any other constant by just doing a majority voting. Okay, and anyway here our constant is A over 9, and so we have A over 9 success probability. Then we want that and now go back to our yes instance and no instance. We want that so I guess what is this thing? Okay, so P is so the projected P. So if projected P is a space where we think we are in a yes instance, and 1 minus P is a no. Okay, so let's write it here. So P corresponds to yes, and 1 minus P corresponds to no. And so we want to have two things, that is, so we are in no instance, then the probability of answer yes is small, or when it's a yes instance, then probability of answer yes is big. I guess maybe a more symmetric way to write this is so because P and I minus P sound to identity, So a much symmetric way to say this, to write this is when it's a known instance, the probability of answer no is greater than A over 9. Okay, so maybe I should write this here. Okay, so yeah, so the probability of being correct is greater or equal to 8 over 9. That's by definition. Okay, so known instance we want to do it on the no projector, and the yes instance it should be on the yes projector. This is a bit going back on. Yeah, hopefully you still remember this is the interpretation on triple one where we have a measurement. So we have a projective measurement, the probability of getting a corresponding outcome is just you have the projector on your state, then non squared. That's the probability. Okay. So yeah, correct probability greater than A over 9. Okay. And then now is our claim. So yeah, so we claim that if there exists any projector P such that give us those two things, okay, then or those two things is the same, okay, then our states must be pretty far away. Okay, so this so now we just call psi TA and this is psi xtb. Okay, so this is for x. So for x, these two things should be pretty far away. So this kta minus kb no square must be greater or equal to 2 over 3. Okay, and yeah, let's see how this work out. No, this is just math. Okay, and yeah, so what we want to do is I think we want to go to inner product between A and B. Okay. So kind of what we show is that yeah, we want to show the inner product with A and B is small. Okay. So I guess the intuition is that you want these two vectors to be pretty far away. So you have the distance big also means the inner product is small because they are unit vectors. So you want this angle to be big. And yeah, the projector kind of means that you have projector here and projector here, etc. Okay. Let's not look at the projector in geometry because it's not helping us. Anyway, we want to show these vectors are two vectors are A and B are far away, and yeah, it has this projector view, and then we have distance big also means the inner product is small. Okay. And let's write down the inner product, known of the inner product, and we have known of inner product is B, and it can be shown small by these two equations. Okay. And yeah, so we have P on A square is less than 1 over 9, and P on B square is greater or equal to A over 9. And we get our P and 1 minus P by breaking identity matrix in the middle. So we can put the identity matrix between A and B and say it's 1 minus P plus P. Okay. Because that's what projection, I guess that's true for any matrix. But anyway, and now we just break it into two different parts of multiplication. Okay. And I guess we first use the linearity to write this thing as absolute value of two terms. So this AB sandwiching 1 minus P and AB sandwiching P. Okay. And then then just by triangle rule of absolute value here, this is less than that's equal to this absolute value plus this absolute value. Okay. And then we stick together the parts we want. Okay. So because we know the B vector is mostly on P and A vector is mostly on 1 minus P. So now we can get the small thing we want. We know 1 minus P on B will be small and P on A will be small. Okay. So yeah, so that's what we write. So this thing is less equal to, we use Cauchy shorts. This is less than known A and known 1 minus P on B and known P on A and known B. Okay. And yeah, and let's see what do we do. Okay, so okay, I think we do something very Okay, we do something very slow here, but at the end we want norm b squared equal to the projection of b on 1 minus p squared and the projection of b on p squared. Okay. So this is what we know from the interpretation of 1 minus p and the p being projective measurement. So this is a probability of projection on p, and this is a probability of a projection on 1 minus p. Okay. And yeah, anyway, but the proof is here. Okay, so if you want to do it once again, so this is the proof of this being projection. But anyway, norm b squared is b is a normalized vector is 1, and that corresponds to the probability should sum to 1. Okay. And yeah, so the middle part is a bit of checking the probability interpretation. So okay, so middle part is a bit of checking probability. And anyway, so here we prove that so if this is large, then 1 minus p on p squared should be small. It should be less than 1/9. Okay, this is kind of intuition we had before. And yeah, so this is small and this is small, and yeah, so the square is less than 1/9, and you take the square root is less than 1/3. So this is less than 1/3, and this is less than 1/3. Yeah. And so yeah, and now we are almost done. Okay. So now we can bound the norm very easy, and the norm A and the norm B is just less equal to 1. So our inner product is less equal to this 1 times 1/3 plus 1 times 1/3, and equal to 2/3. Okay. Okay. So now I bound our inner product is away from 1, although it's not so small. Really 1 is close to 0, but anyway, it's not 1, so that's good. Okay. And then we can bound the distance by lower bound on inner distance by our upper bound on inner product. So we just multiply this out. Okay. So this is a squared plus b squared minus ab inner product minus ba inner product. And yeah, this is greater or equal to 2 minus 2 times the because this thing is so this thing is actually a real number, so it makes sense to write the greater or equal to, and then you take an absolute value, it can be only bigger. So yeah, yeah, it's a bit complicated because those two can be complex number, but this is actually 2 minus so this thing is actually equal to 2 minus 2 times the real part of AB. Okay. And then you take the norm of AB is greater than the real part of AB. So yeah, so this is getting smaller. Okay. And yeah, then finally we can use our bound on our inner product between AB. So it's greater or equal to 2 minus 2 times our 2/3, and you do this arithmetic is 2/3. Let's see, yeah, and so let's basically complete our proof here. So so we have our claim here being proven. Then we just need to plug things. So we want our A to be psi t and B to be psi xt, and so we see that if you have any p that distinguish A and B in this way, then our A and B then our psi t and psi xt must be pretty far away, and this is true for all x. Okay. And so each one of them is big, then you sum over them, then it should be at least n times this 2/3. Okay. So yeah, so here is our proof that our dt is omega n. Okay. And yeah, and so combining, so go back a few slides. So now we get our 2 and our condition 2. Also get prove that at the end the progressive function needs to be pretty big. And also from 1 we know it don't grow too fast, So we know that we need at least omega square root n steps to do the search problem, even with quantum oracle. Okay, and let's stop here today. And on Tuesday we'll give basically a better bound on this theorem. So we'll show just a flash one slide, I guess. Let's see, do we have here? Okay, yeah. So next time we are going to prove that actually get a better bound on this inner product. So inner product is actually between the square root epsilon, square root epsilon times 1 minus epsilon. Okay. I think the boundary we got here is square root epsilon. So we'll get our extra square root 1 minus epsilon back. Okay. So yeah, then we can have better bound. So see you next time.